Okay, so this section 4.2 basically put together whatever we have in 4.1 into a graph, plus on the top of that we'll put more details. Now let's see, 4.1 number 33, let the rational function be x squared minus 3x minus 4 over 2x squared plus x minus 1. The first thing you will do is to factor them. Now at this point, if you don't know how to factor, I cannot forgive you anymore. You need to know how to factor. Okay? You need to know how to factor. And then the denominator, it will be 2x and x plus 1 here, minus 1 here. So this will be the simplified form will be x minus 4 over 2x minus 1 for x not equals to -1. It will be undefined. In fact, it is a whole at x equals to -1. From here, then we see the domain is all real numbers except 1/2 and -1. The y-intercept is you see R0, right? R0 equals to -4 over -1, that's 4. So the y-intercept is 0, 4. The x-intercept, we will look at the numerator of the simplified form. X minus 4 is 0, so x equals to 4. So x-intercept is 4, 0. Vertical asymptote, let me do it up there. For the vertical asymptote, we look at the denominator of the simplified form. That's x equals to 1/2. And then horizontal asymptote, because they have the same degree on the numerator and denominator, then the horizontal asymptote will be the leading coefficient over the leading coefficient. Now, as an extra, let's put in one more. Find the coordinate of the whole. Find the coordinate of the whole. The whole will be at x equals to -1, but you plug that into the simplified version. That will be -5 over -3, that's 5 thirds. So the coordinate of the whole will be -1, 5 over 3. Now let's put things together. Start with the y-intercept is 0, 4. That's the y-intercept. Oh, by the way, if you are, I assume you will be printing your tests, right? Okay, especially for test 4. Especially for test 4. But if you are writing down your test later on, some people don't have printer, then try to at least print some graphing paper or get some graphing paper. Okay, that way then your graph will be well scaled. Unless I say you don't need to graph it to scale, then you can just do it on, you don't need a graphing paper. Okay, that's the y-intercept. X-intercept is 4, 0. Horizontal asymptote, y equals to 1/2. Y equals to 1/2. That's y equals to 1/2. And then vertical asymptote is x equals to 1/2. Oh, wow, okay. Happens to be both 1/2. Huh? So This is x equals to 1/2. And the whole is at -1, 5/3. So -1, 5/3. That would be here. That would be the whole. 5/3 is approximately 1.67, approximately. Okay, now then I will connect those graph. I will start from horizontal asymptote, right, on the very far right. Okay, and so it will be approximately like this. From horizontal asymptote, I hit this hole, go this way, and then go up there. Okay, while on the one on the right, I start from horizontal asymptotes going down, like this. Okay, approximately that's what it looks like. Now, of course, if you want to be more detailed, you may want to put more coordinates. Like for example, the one here, right? If you may want to put, for example, what happened at x equals to 1. So you put more coordinates. What is r star 1? R star 1 will be 1 minus 4 over 2 times 1 minus 1. That's -3 over 1. That's -3. So at x equals to 1, the y is -3. How about when x equals to 2? So r star 2 will be 2 minus 4 over 2 times 2 minus 1. That's -2/3. Approximately. So you see, that way then we can refine our graph a lot better. Okay, at least that's what we get right now. We can actually put more details, even more details into this. So I basically put together what you have learned from 4.1 and put together into the graph. Okay, but now I want to teach you more into the analytic part. For example, maybe I use blue. Find the horizontal asymptote intercept. So basically, does the graph intersect horizontal asymptote? If so, at what coordinate? Okay, basically, I try to show you how to do computationally, that the graph here does not intersect with horizontal asymptote. You see, the way I graph it, my graph in red does not intersect the horizontal asymptote, right? Okay, but we know that the graph may intersect horizontal asymptote. The graph will not intersect vertical asymptote, but may intersect horizontal asymptote. The question is, how do we find out? Then what you will do is you set them equal to. Okay, you set them equal to. So you set the simplified version, x minus 4 over 2x minus 1. Okay, set it equals to the horizontal asymptote, 1/2. Okay, if there's any horizontal asymptote intercept, then there must be some x for that. Okay, now I will do cross multiply here. I get 2 times x minus 4 equals to 2x minus 1. So I get 2x minus 8 equals to 2x minus 1. I end up with -8 equals to -1, which is a contradiction. So from there, then we see no horizontal asymptote intercept. Okay, so you see that the graph will intersect horizontal asymptote when they are equal to each other. Does it make sense? Okay, now another tool that we already know, is how do we know if the graph is above or below x-axis? Now that one we actually already know. Or below x-axis. That one we already know. We will not do it for this question because it's actually quite clear. But we basically set the rational function, the original rational function, okay, and find the sine graph. Maybe I should say simpler way. Find the sine graph of Rx. Find the sine graph of Rx. Okay, remember the way we solve nonlinear inequality? Now the second step, find the sine graph, help you to see where positive means above f-axis and then negative means below x-axis. Okay, it's already factored, right? So you can actually just easily find the sine graph for that. In fact, we can go further asking the next question. How do we know if the graph is above or below horizontal asymptote? And that way, for that, you will use find the sine graph of Rx minus horizontal asymptote. Okay, but we will apply that to other question. I go on to 4.2 now. Let's say I work on question number 26 on 4.2. I will do plenty of problems from this section. Let gx be x over x squared minus 9. I will factor it. This is x over x plus 3, x minus 3. Actually, let me put a side note. Note that g negative x happens to be, okay, is negative x over negative x squared minus 9. That's negative of x over x squared minus 9. That's negative gx. Now, because g negative x is negative gx, then gx is what kind of function? That's an odd function. And the graph has origin symmetry. It would be quite helpful. Okay, now then part A, what is the domain? You need to factor it first. It's all real numbers except -3 and 3. Okay, and then part B, how about the y-intercept? The y-intercept, you will see that 0, 0. Likewise, the x-intercept, also 0, 0. Vertical asymptote, x equals to -3, x equals to 3. Horizontal asymptote. The degree on the top is higher than the degree at the bottom. So horizontal asymptote is y equals to 0. Okay, now then, there's no hole. Let's start graphing it. Okay, so x-intercept, y-intercept both origin. Okay, horizontal asymptote is y equals to 0. That's the x-axis. So let me draw it this way. Vertical asymptote, x equals to -3. And x equals to 3. Now the thing is, with only these, we cannot do much with the graphing though. Okay? With only these, we cannot do much. We only have x and y, which happens to be the y-intercept, and we know it has origin symmetry, but nothing more we can say about that, right? Okay, you can do plotting. You can get what will x equals to 1, x equals 2, x equals 4, 5, 6, 7, right? But it will take too long. In my opinion, it's better for us to do the sine graph. So let's do the sine graph, part F, sine graph. We have the critical numbers at x equals to 0, that gives us 0. At 3, give us undefined. At -3, that gives us undefined. Okay, now we see here this will be positive, negative, positive, negative. It means from very, very far on the left-hand side, even though we start from the horizontal asymptote, we know it will go down. Why? Because it's below x-axis. It's negative, right? On this -infinity to -3, it's below x-axis. Okay, now and then from -3 to 0, that's above x-axis. But don't forget, we have vertical asymptote. So I will start from here, right? Like this, maybe. And because of the fact that it is an odd function, then I actually reflect that with respect to the origin. So later on, it will look like this. Okay, where from 0 to 3, it's below x-axis, and from 3 to infinity, it is above x-axis. Again, if you do plotting, it will take you forever. Okay, you get more accurate data, but a lot slower though. Okay, while at this point we actually focus more about the behavior of that graph. Okay, yeah. Of course, it's nothing wrong if you want to choose. Let's say when x equals to 1, what happened? When x equals to 2, what happened? So on and so forth. Okay. From here, I already show you how do we get the sine, how do we know the graph above or below the sine graph. Let's do more. That's number 26. Let's see number 34. 34, let gx equals to 2x squared, I'm sorry, x squared minus 2x minus 8 over x squared minus 9. Always factor first. Always factor first. X minus 4, x plus 2 on the top, x plus 3, x minus 3. Nothing cancels, so no holes. The domain. All real numbers except negative 3 and 3. Part B, up at the y-intercept. Y-intercept is 0, 8 over 9. X-intercept will be 4, 0, negative 2, 0. Now, do you think the way I do it is too easy? Or do you know what I'm doing here? Okay, no response. Okay, here's the thing though. There are a lot of things to consider when it comes to graphing rational function. Okay, but once you get, if you practice well, then for each one of these questions, you know what to look at. There are many things you need to look at, but for example, for the domain, you look at what? The denominator of the rational function of the denominator, right? Okay, the domain, basically no more work, to be honest with you. All you need to do is actually from here, all you need to do is actually factor. Okay, and then once you factor, then you need to know what to look at for what question. For example, the domain should be all real number except the 0 of the denominator. Just look at that, right? Okay. Second, what I want to say is this: you want me to show work, I can show you work. Okay, but it is not fair that when I show you work, but all of a sudden in your test you don't show me work. On the other hand, right now for this type of question, all the work you need to do is actually factoring. What happens after that? You need to know what to look at, but no more work. Okay, for example, the y-intercept. How do you see the y-intercept? That's constant over constant. 0, 8 over 9. And if you usually know how to skip steps, why can't you skip steps right now? Right? Okay. Now the third one, how about the x-intercept? The x-intercept, you look at the numerator. Okay, it's about what to look at. Okay. What happens to the negative for the y-intercept? What negative for the y-intercept? It's negative 8 over negative 9. Negative 8 over negative 9. That's positive 8 over 9. Okay, so negative 8 over negative 9, that's negative over negative is positive. So yes, you need to know what to look at. You need to know what to look at. But the first step, the most crucial step is to factor. The thing is this though, when I give this test in the past, and also this kind of question in my pre-calculus class, most of them didn't factor. Most of them didn't do this first. Okay, and then they try to show so much work here, but no, you actually factor first. Once you factor, okay, then as long as you know what to look at, you know what to do. Okay, so the only time you don't know what to do is when you don't practice enough. And I'm sorry, that one I cannot help you. I cannot do the practice for you. I did my practice, but that's only for me. That's something you have to earn yourself. Okay, good thing this is for test 4 though. Okay, not for test 3. For your test 3, you need to be practice for your polynomial, right? Okay, but again, you may say, you may try to cheat by using graphing calculator or using photomath. Trust me, you won't. Learn from your test tool. It doesn't help. Okay, now it doesn't help. You need to really know something. In the case where the function has no constant, will the y-intercept be 0, 0? What do you mean by have no constant? It always have constant. then the constant is 0. If the 8 and 9 not there, then it's 0 over 0. Right? But 0 over 0 is undefined, therefore there's no y-intercept. Suppose you have x squared minus 2x over x squared, right? If the 8 and 9 not there, well, implicitly the constant are 0. So to say that what happened if the constant not there, the constant always there. The constant always there. Okay, you just don't see it if that's 0, right? But if you have this situation, you will see the domain will be all real numbers except 0. So 0 is not in the domain, automatically there's no y-intercept. Right? Okay. That's if you have 0 over 0. But if you have, let's say, 0 over 8, then the y-intercept is 0, 0. By the way, that's what we did in the previous question. Let's look back a little bit. Yeah, that's what happened here. What happened if you don't have constant? Well, you simply don't see it, but it doesn't mean it's not there. Okay, that's the same argument with, by the way, God, though. Simply because you don't see God doesn't mean the God is not there. You know, of course, there are things that you don't see means it's not there, but that's that way of argument does not hold. Okay, somebody once said that to me, that Thomas, I don't see your brain, so you have no brain. You're fine. I still teach you. Okay. Well, anyway, so the constant is always there, but if you don't see it, then it means the constant is 0. Okay. Yeah. Now, the issue, I think, is more into what happened if the constant on the denominator is 0. If the constant on the denominator is 0, then what happened? Right? Oh, I think I can do this. One second. I need to erase these. How about the part D? How about the vertical asymptote? What do you look at? You may say show work, but there's no more work. You already did the factorial, if you do the factorial. The vertical asymptote is the 0, x equals the 0 of the denominator. So we have two vertical asymptotes here. How about horizontal asymptote? They have the same degree, so y equals to leading coefficient over leading coefficient. Horizontal asymptote is y equals to 1. Now, let's put that into graph. We may need to put more details later on, but let's have this for now. So the y-intercept 0, 8 over 9, almost 0, 1. So this is the y-intercept. X-intercept 4, 0, and negative 2, 0. Vertical asymptote, x equals to 3, x equals to 3, and x equals negative 3. Horizontal asymptote, y equals to 1. I can't really tell right now. I can suggest that it will look like this. It will look like this later on. But I do this based on my experience. I know that's what it will look like. Okay, let me do this analysis with you. Hopefully you can follow. But the better way to do this is by doing sine graph. Okay, We know that this is horizontal asymptote, so the graph must go from here, right? Now the problem is, will that go up or will that go down? Will that go up or will that go down? The thing is, if it were going down, then you must have an x-intercept here, which you don't, right? So it won't be going down, it must be going up. Okay? Next, notice that this critical number x equals to -3, the critical number x equals to -3, is a critical number with multiplicity of 1. So it must change sign. From positive becomes negative. Okay, now I can only go that far. From the right-hand side, on the other hand, I know I need to start from horizontal asymptote. Either it goes up or goes down. Now, which one supposed to be? Well, if it goes up, there would be no x-intercept, right? But we do have an x-intercept, so it must go down. Also, x equals to 3 is a critical number with odd multiplicity. So on the right-hand side, it will change sign. That's how I know it will be like that. Okay, now to help us better, it would be nice if we can use sine graph. So let me apply sine graph here. Let me do the sine graph. So part F, sine graph. Critical numbers are 4, 3, -2, -3. The sign with plus, minus, plus, minus, plus. All of them with multiplicity of 1, right? So we know 4 to the right will be positive. Between 3 and 4, there will be negative. Between -2 to 3, that will be positive. From -3 to -2, that will be negative. And from -infinity to -3, that will be positive. Like that. Okay, further analysis, part G. The graph above or below horizontal asymptote. So I need to see the sine graph of the rational function, which is, what's that again? Rational function, it's x squared minus 2x minus 8 over x squared minus 9 minus horizontal asymptote y equals to 1. Now, do the sine graph for this. So x squared minus 2x minus 8 minus x squared minus 9 big over x squared minus 9. That will be x squared minus 2x minus 8 minus x squared minus 9 over x squared minus 9. So don't forget to use parentheses here. Don't forget to use parentheses. I did the LCD, x over 1 over 1. And then this will be -2x plus 1 over x squared minus 9. I need to find the critical numbers. The critical numbers are -3 and +3, both give us undefined, and +1/2. Oh, okay. So if that's the case, we know that the horizontal asymptote intercept here, the horizontal asymptote intercept here must be, the coordinate is 1/2, 1. How do you know it's 1/2, 1, Thomas? From the x we know, it's 1/2. How about the 1? Well, that's the horizontal asymptote, right? Y equals to 1. Okay, and then how about the sine graph? You will see that this is, when you do plug the numbers in, you will get negative, positive, negative, positive. So to the left of -3, it will be above, to the left of -3, it will be above horizontal asymptote. You see, to the left of -3, above horizontal asymptote. Okay, now between -3 and 1/2, that's below horizontal asymptote, below horizontal asymptote. Okay, and then between 1/2 to 3, that will be above horizontal asymptote. And between 3 to infinity, it will be below horizontal asymptote. Okay, so that's how we do the analysis. Now, this thing that I did here, simplifying rational expression, is something we learned in chapter review. Okay, so long time ago, long time ago. That's the reason I went over that at that time, though, chapter P. Okay, now that's for this one question. Let's do more. Let's do more. I would like to do one more problem before I go on to the slant asymptote case, where I will do 2 more problems. Number 38 seems to be super difficult. Number 38, I think you can factor the top, but I don't think you know how to factor the denominator. Let fx equals to x squared minus x minus 2 big over x cubed minus 2x squared minus 5x plus 6. I know how to factor the top, but I don't know how to factor the denominator. How do we do that? Well, the denominator is a polynomial, remember? Right? And to factor a polynomial, then you come into that play of finding the zeros. Okay, so let me use the green color. This is x cubed minus 2x squared minus 5x plus 6. You use the technique I taught you in chapter 3. Okay, we will have 1 positive zeros out of 3 zeros. And if that zeros is a rational, then it will be plus minus 6 over 1 plus minus 1 plus minus 2 plus minus 3. A factor of 6 over a factor of 1. So let's try. What number should we try as a candidate? Let me try, I do this by guessing. Let me try 2. 1, 2, 2, 0, 0, -5, -10, -4. Uh-oh. Oh, hold on. When x equals to 0, the y is 6. When x is 2, the y is -4. By intermediate value theorem, there must be a 0 between 0 and 2. There must be an x-intercept between 0 and 2. Let me try 1 then, because 1 is between 0 and 2. So you will start by guessing, right? You will start by guessing. Actually, Why am I thinking too hard? Notice that when I add the coefficients, it's 0. That means 1 is a 0. That means 1 is a 0. Duh. So 1, 1, negative 1, negative 1, 6. This is negative 6, 0. So I can factor x minus 1 here, and then that x squared minus x minus 6 will factor to be x minus 3, x plus 2. So x minus 3, x plus 2. Okay, so we can start. Once we fully factor them, we basically done. We just need to write down all the details. The domain is all real numbers except 1, 3, negative 2. Part B. How about the y-intercept? When x equals to 0, the y is negative 2 over 6, simplified to be negative 0, negative 1/3. How about the x-intercept? 2, 0, negative 1, 0. Vertical asymptote. Wow, we have a lot of asymptotes here. X equals to 1, x equals to 3, x equals negative 2. Horizontal asymptote. The degree on the top is less than the degree at the bottom, so y equals to 0. Let's do the sine graph to help us seeing if the graph will be above or below x-axis and where. Negative 2, that's undefined. Negative 1, that's 0. 1, that's undefined. 2 is 0. 3 is undefined. And that will be plus, minus, plus, minus, plus, minus. Things together. Y-intercept 0, negative 1/3. It's very close to the x-axis. X-intercept 2, 0, negative 1, 0. Vertical asymptote x equals to 1. X equals to 3. And x equals to negative 2. Wow, very minimum information basically. Then, to the left of negative 2, that's negative, means it is below x-axis. So it will be from horizontal asymptote y equals to 0 going back. And then, between negative 2 and negative 1, that will be positive. From negative 1 to 1, that will be negative. From 1 to 2, that's positive. And from 2 to 3, that would be negative. And then from 3 to infinity, that will be positive. But we have horizontal asymptote, so that's what we will do. Now, last part. Slant asymptote, also known as oblique asymptote. Slant asymptote is the asymptote, the linear asymptote, it's a line, okay, whose slope is not zero nor undefined. In other words, this is not vertical asymptote nor horizontal asymptote. Okay, now we have slant asymptote. The graph of a rational function has slant asymptote if the degree on the top is exactly one more than the degree at the bottom. If the degree on the top, n, is one more than degree of the denominator, m. Now, let's say, for example, I pick question number number 62. Number 62, let fx equals to 2x squared minus 5x plus 5 big over x minus 2. Oh, shoot, the top one I cannot factor. The top one I cannot factor. But you see the degree on the top is more than the degree at the bottom. So you see n equals to 2, but the m equals to 1, right? The degree on the top is 1 more than the degree at the bottom. So if I need to find the slant asymptote, how to find the slant asymptote, it must be y equals to mx plus b. Okay, now how to find that? We actually divide the numerator by the denominator, 2x squared minus 5x plus 5 over x minus 2. Okay, you actually divide it. Or because the denominator here is binomial, x minus 2, so I can divide using syntactic division. So the quotient 2x minus 1 will be the slant asymptote. Okay, that's the slant asymptote. That's basically the only thing new for you. Let's put them together now. Part A, what's the domain? Okay, that's all real numbers except 2. How about the y-intercept? When x equals to 0, the y will be negative 5 over 2, which is 0, negative 2.5. Part C. How about the X-intercept? Now notice that I could not factor the numerator, but doesn't mean it doesn't have X-intercept. We don't know yet. We don't know yet. Okay. We need to solve, set the numerator becomes 0. We need to set the numerator to be 0. Px, the numerator, we need to set that to be 0. One way to solve that polynomial to be 0 is by factoring, but that's not the only way. Other ways are completing the square or quadratic formula. Now, let me use quadratic formula here by first computing the discriminant. Discriminant is negative b squared minus 4ac, which is 25 minus 40, that's negative 15. So no real zeros. There are complex zeros, but no real zeros. From there, we say no X-intercept. Now, you should not just tell me no X-intercept without giving me reason. If you say none, then I will ask you why. Okay, but here we have no X-intercept. We have vertical asymptote. Part B, vertical asymptote is X equals to 2. Horizontal asymptote, the degree on the top is more than the degree at the bottom, so we don't have horizontal asymptote. We have slant asymptote instead. Now let's put things together. Put it here. Y-intercept 0, negative 2.5. 0, negative 2.5. No X-intercept. Vertical asymptote, X equals to 2. No horizontal asymptote. But the slant asymptote is 2x minus 1. 2x minus 1, the y-intercept is 0, 1. The slope is 2. So it looks like is approximate. Okay, that's what it looks like. Now, unfortunately, that's only one part. Even if I do sine graph, I only know that it will be, if I do sine graph on 2x squared minus 5x plus 5 over x minus 2, you have only one critical number. And that will be plus here, minus here. So we know that to the right of x equals to 2, it will be above x-axis. To the left of x equals to 2, it will be below x-axis. Okay. We also know that it will be from horizontal from the slant asymptote. So it will come from here. My guess is it will look like this. My guess is it will look like this. Okay, but that also means I need to show that the graph is below slant asymptote to the left of that vertical asymptote, and it will be above the slant asymptote when x is to the right of 2. So how about the sine graph on slant asymptote? So 2x squared minus 5x plus 5 over 2x minus 2 minus 2x minus 1. This is the rational function, And this is the slant asymptote. Let's simplify that first. So this will be equals to 2x squared minus 5x plus 5 over x minus 2 minus 2x minus 1 times x minus 2 over x minus 2x squared minus 5x plus 5 minus 2x squared minus 5x plus 2 over x minus 2. So your algebra has to be good already. And then when I subtract, I get 5 plus minus 2. So that would be 3 over x minus 2. So the sine graph will only 2 for 0 here is positive here. So to the left of x equals to 2, to the left of x equals, this is x equals to 2 here. This vertical asymptote. To the left of that, the graph will be below slant asymptote. And to the right of that will be above slant asymptote. Don't forget the graph should approach the slant asymptote when we go to positive infinity. It will get closer to the slant asymptote as we go to positive infinity and when we go to negative infinity. Okay. That's for number 62. Let me do one more, number 64. Yeah, I will convert this to PDF and put it on the discussion board later on. Number 64, let fx equals to 2x cubed plus x squared minus 8x minus 4 big over x squared minus 3x minus 2. Now you need to know how to factor the top. Actually, that happens to be quite factorable. So it should be plus 2 underneath. So x minus 2, x minus 1. Now on the top, I believe you can do factorization by grouping. Yeah, I believe you can do factorization by grouping. You will get x plus 2, x minus 2, and then 2x plus 1. That's if you factor it. Oh, x minus 2 cancel. Nice. Okay, so the simplified version, f star again. The simplified version will be x plus 2, 2x plus 1 over x minus 1. For x not equals to 2, it will be undefined. Undefined when x equals to 2. That will be our whole. Let's do that first. So the side note, the whole will be f star 2. So I plug this undefined one into the simplified version. Okay, that's how I get that. That's how I know that's what I need to check. So this will be equal to 2 plus 2 times 2 times 2 plus 1 over 2 minus 1. Oh, so that will be 4 times 5, that's 20. Oh, okay, so the whole is located as 2 comma 20. Okay, the domain is all real numbers except 2 and 1. The y-intercept at 0, -4 over 2, which is 0, 2. The x-intercept, look at the simplified version, is, so that would be -2, 0, -1/2, 0. Vertical asymptote is x equals to 1. Horizontal asymptote, the degree on the top is more, so there's none. But the degree on the top is 1 more than the degree at the bottom. So I can find the slant asymptote. The slant asymptote, let me look at the simplified version. This is 2x squared plus 5x plus. Okay, so that's 2, 5, 2 divided by x minus 1. So this is 1. So the slant asymptote is given by y equals to 2x plus 7. Let me try to graph that without scale, because otherwise I need a big graphing paper. The y-intercept 0, -2, so let's say it's here. X-intercept -2, 0, -1/2, 0. Vertical asymptote x equals to 1. Here. Vertical asymptote x equals to 1. Horizontal asymptote is not there. And then the slant asymptote is 2x plus 7, something not right here. 2x plus 7, it's approximately like this. Yeah, it's approximately. It's y equals to 2x plus 7, unless I computed it incorrectly. But something not right here. Yeah, something not right here. Now I know what's wrong. This one, I placed this x-intercept incorrectly here. This one is incorrect. Okay, it should be -1/2, like this, should be like this. Now it's better. Okay, so the graph later on will be from slant asymptote going this way, going this way, going down here. -2, -1/2. This is -2 here, and my graph will be, let me use okay. And then on the right hand side, I will have something like this. Okay. But when x equals to 2, 20, we have slant, we have 4. Okay. Now, your suggested homework from this 4.2 I would like you to try number 20, sorry, not 20, not an odd number. I would like you to try number 19, 21, 25. I don't need you to do all of them though. 33, 37, 41, and then number 55, 57, 61, 62. Okay, now what you need to answer are the questions I usually ask: the domain, the y-intercept, x-intercept. So we just borrow the function. Okay, horizontal asymptote, vertical asymptote, vertical asymptote, horizontal asymptote, slant asymptote if the degree on the top is one more than the degree at the bottom. Okay, and if you have a chance, you can do the sine graph. Okay, sine graph of the rational functions, and consider about the horizontal asymptote intercept. If you have horizontal asymptote, slant asymptote intercept if you have slant asymptote. And then graph it. Okay, now that's where we're gonna go with that chapter 4. I will not go on with conic section. For the rest 15 minutes, I will start 5.1. Exponential function. Exponential functions. And their graphs. Okay, let me start with basic exponential function. Basic exponential function has the pattern or has a form fx equals to a to the x, where a has to be positive and cannot be 1. Now I will explain much later why this cannot be negative and cannot be 1 and even cannot be 0. Okay, I will not explain it now. On Thursday you have a test, so on Tuesday when we come back, then I will explain it further. Okay, but the focus here will be on the graph first. Okay, I usually start, when I teach this part, I usually start with graphing, plotting. Plot fx equals to 2 to the x. We want to graph it by plotting. So what it means? It means I want you to create a table of x, y, and therefore the coordinate x, comma, y. So when x equals to 0, 2 to the 0 is 1. So the coordinate associated to that is 0, 1. When x equals to 1, the y will be 2 to the 1, that's 2. The coordinate associated to it is 1, 2. When x equals to 2, that's 2 squared. For the y, that's 4. Now you see the following phenomena. If I try to sketch the graph, you will see the following phenomena at 0, 1, 1, 2, 2, 4. Because the base is 2, then every time you move 1 unit to the right, you will multiply the previous value by 2. So when at 0, when x equals to 0, the y is 1, right? So when you move 1 unit to the right, the 1 multiplied by 2 becomes 2. You move another 1 unit to the right, the 2 becomes 4. Move another 1 unit to the right, the 4 becomes 8. Like that. Does it make sense? That's if the base is 2. Now, you will see with the same principle, when I move to the left 1 unit, instead of multiplying by 2, if we go to the right, when you go to the left, you divide by 2, divide by 2, divide by 2. Okay, and you can check that by computation. When x is -1, 2 to the -1 is 1/2. When x is -2, the y will be 2 to the -2, which is 4. Okay, so the graph will look like this. The graph will look like this. Okay, the graph will look like that. Now, the coordinates where I put a yellow highlight are coordinates you need to give me every time you graph exponential function. Because the base is greater than 1, then we see the following. Because the a is greater than 1, then the graph is increasing. And because this function is increasing, then this function, from what we learned in chapter 2.7, because the function is increasing, then the function is 1 to 1. You can try. Every horizontal line will touch the graph at most at one point. Okay. Now we see the following important ones. The domain of this function is all real numbers. The range is from 0 to infinity, but not including 0. See, every time you move to the left, you keep on dividing by 2, dividing by 2, dividing by 2. So it gets very, 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 very small, but it will not be 0. Why? Because any positive number you pick, you divide by 2, it will still be positive. Every time you divide by 2, it will still be positive. Smaller and smaller, but it becomes positive. Still positive. Okay? So you will see the range will never be 0, including 0. No. Very close to 0, but not 0. With that said, then we notice that we have horizontal asymptote. Y equals to 0. Okay. Furthermore, we have y-intercept 0, 1, no X-intercept. Now, the thing is, this principle applies for all base greater than 1. For all base greater than 1. Let me show you if I use my graphing software. So what we have done just now is y equals to 2 dx. That's what it looks like. I can screenshot this later on. You see, however far you go to the left, I can super zoom this, and you see the graph is not touching. It's not touching x-axis. It seems like it's touching, but it's not. It seems like it's touching at y equals to negative 9.3, but if I zoom that further there, you will see it's not touching. It's very, very close, but it's not. You see, it's not touching it. Right? It's not. It's very, very close, but it's not. Right? So we confirm that. Okay. Now let me change that base 2 becomes base 3. What happens if we have base 3? Now we expect, because the base is 3, then when we move 1 unit to the right, then we will multiply the previous value by 3 instead of by 2. So you see what happened here. The red one is the graph for 3 to the x, right? So when x is 0, the y is 1. When I move 1 unit to the right, I multiply that 1 by 3. Multiply by 3. Multiply by 3. So when the base is greater than 1, it will be increasing. Okay, the y-intercept still 0, 1. The domain and the range stays the same. Okay. In fact, let me make the base to still be greater than 1, but slightly greater than, and see how it behaves. Let's say y equals to 1.2 to the x. See, it is still increasing, right? It's still increasing. Still increasing. Let me screenshot this. Put it back one. This is y equals to 2 to the x, y equals to 3 to the x, and this is y equals to 1.2 to the x. Now all of them has the same situation, that the domain is all real numbers. The range is from 0 to infinity, not including 0. Horizontal asymptote on the left-hand side, y equals to 0. The y-intercept is 0, 1. No x-intercept. The function is increasing. And because it is increasing everywhere, consequently, the function is 1 to 1. Now, let's go back to our graph, the basic graph. What happens if the base is less than 1 but still positive? happens if the base is less than 1 but still positive? Let's say if I have the base to be 0.5. What happens if the base is 0.7? What if the base is 0.1? I think that would be quite steep. Y equals to 0.1. Okay, let me screenshot this. That way, then we can analyze something. What we have here earlier, when the base is greater than 1. Now, the one below here, that's if the base is still positive, yet is less than 1. We see that the domain is still all real numbers, the same with the case we had before. The range is still from 0 to infinity, the same with what we had before. We have horizontal asymptote, still the same, y equals to 0. Y-intercept is still 0, 1. X-intercept still none. The difference is now that it is decreasing. Now, even though it is decreasing, in fact, once the function is increasing or decreasing, then the function is 1 to 1. Okay, if I put more details, this is 0.1 to the x. This is 0.5 to the x. This is y equals to 0.7 to the x. Now, what I want you to do is to memorize the facts that I give you in this 5.1a, such that on Tuesday next week, when we come back, we can finish this a lot faster. Okay, and I would also like you to read. So read suggested homework from here. Read 5.1 and 5.2. Do this after your test. Okay, this is where I will stop.